Yeah, hello everybody. Thanks for joining us in this late hours. Yeah, we are Nicola from Bel Power Solution. This is Menno from Circle B, and I'm Sam. I'm with Rittal, and we did an FEM simulation about the power distribution in a 12-volt OCP rack. And yeah, the reason behind is that we have several requests for higher load in a 12-volt OCP rack, and we did testings before, and we know that the clips of the servers are the weakest point in the power distribution system in the rack, but we did not have so much information about the busbars and how much load they could handle. And so we started this, and now we want to present you the results. Yeah, I will hand over in a second to Menno. Yeah, so he will follow me with the rack configurations. We did several rack configurations with several loads, and then Nicola will go further with the FEM simulation models and results and the conclusions. Yeah.
Okay. I have a microphone. So typically when we design an open rack layout, we also calculate what we expect in terms of the power draw. And we try to stay within this 6.6 kilowatt limit per bus bar. So here in the calculation, you see there are calculations for 2 zones. We'll try to point it out. Here is what we calculate as the maximum power that will be used per zone. So you see that it's well within the 6.6 kilowatt. When we take the maximum wattage per server just from the data sheet that the manufacturer indicates. And when we use a 1U power shelf, then in a 3+3 configuration with 3 kilowatt power supplies, we are still within this limit of the power shelf as well as the limit of the bus bar. But we have a lot of empty space. We're putting in a lot of these dummy nodes. You have probably seen the carton boxes here somewhere. Blank plates, dummy nodes, that's what we use to fill up this empty space. When we configure a rack with only compute, of course, there's no storage mix in this, so this is just compute in the rack. So this is the typical configuration that we would make for a customer. Now, if we go a little bit further, if we try to fill the whole rack with the vendor specified maximum wattage, then it would look like this. We are using like almost 10 kilowatt in the top power zone. But we could still do that if we do the 3+3 configuration with the 3.6 kilowatt PSUs. So it's still within the limit of that power shelf with those PDUs. The third thing we calculated is if we look at the Tioga Pass server specification, it says the maximum TDP of the CPU is 165 watt. So again, we did the calculation, and you'll see that in the top power zone, we are at a little bit more than 12 kilowatt. So if we put the power shelf in a 5+1 configuration with 3 kilowatt PSUs, then we're still within the limit of the power shelf, but we are like way above the specified 6.6 kilowatt of the bus bar. So another configuration is an example with 1 GPU instead of 2 CPUs. It's similar calculation as the previous one. And then if we look at the CPU supplier, they also have in this socket, they have a 205 watt CPU. So if we take that, then we're at like almost 15 kilowatt for the highest power zone. It's still possible with this 1U power shelf if we do the 5+1 configuration with the 3.6 kilowatt power supplies, then we have 18 kilowatt limit per zone. But it's way above what the design is for the bus bar. So I will now hand over to Nicola.
Okay. So basically, the idea here was to simulate these conditions that Menno just explained, to understand if the bus bars of the power shelf and the bus bars of the rack are still within their thermal limits. We have used ANSYS multiphysics, which is coupling basically Maxwell, which is an electromagnetic program, finite element program, to simulate the current distribution, together with the spec. And by doing that, we are able to simulate both losses and temperature of the bus bars. So going forward here, you see the simulation setup. What we did, basically, we have measured the airflow of a single server, and then we set up the simulation with half of this airflow, because we know that obviously you don't want to run the fan at full speed. This is just an assumption. Obviously, you could run the fan at higher speed if you want. And so we get an airflow per server of 30 liters per second. And if you consider 30 servers in the power zone, it's 90 liters per second, and a speed of 3.6 meters per second. While the airflow in our power shelf is about 38 liters per second, and the speed 1.7. The other pictures show the mesh. You know, we tried to make as much as precise meshing for the simulation to get as much as accurate results. The next slide here shows the simulation setup and the temperature limits. Basically, we have considered the Open Rack standard 2.0, 3 millimeter bus bars, the one that are currently implemented also by Facebook. The standard clips have a nominal resistance of 0.3 million, and we have considered a cold aisle temperature of 35 degrees. So the air coming inside 35 degrees, which is considered to be on the maximum temperature that you could have in a data center. The temperature limit of the bus bars, according to UL, is 90 degrees if the bus bars are plated. Then here you see the norms of reference. It's 70 degrees if the bus bars are not plated, but in our case, it's 90 degrees. Now we started directly with a simulation of the configuration number 3, because the first two were, the first one was already tested. The second was also not exceeding too much the nominal condition. We wanted to see already in a configuration which has never been tested how the bus bars would behave. In this case, the rack is a 23.4 kilowatt, so it's quite high power already. And the load for the current load in the top power zone is more than 1,000 amps. You'll see that basically that in this condition, the bus bar power losses are approximately 20 watts, and the hotspot is only 58 degrees Celsius. And so there is a lot of margin versus the 90 degree, which has been set by UL as a limit. And also the bus bars in the power shelf, obviously all the current goes through the bus bars of the power shelf, have a bit more losses, 34 watts, and the hotspot is about 65 degrees Celsius. The clip losses are approximately 2.9 watts for every clip, and these losses have been considered in the thermal simulation. So they contribute to eat up the busbars. The configuration 4 is basically the same as configuration 3, so I'm not losing too much time on that. It's basically the same, just a little bit less power, so very, very similar results. This is a little bit different because configuration 5 is really getting up to the limit. And as you can see, the pictures are turning to red, means that the temperatures are getting higher. And we have 1,200 amps in the top power zone coming from our power shelf. And the busbar temperature, in this case, achieve approximately 72 degrees Celsius, and the losses of these vertical busbars is 29.3 watts in the top power zone. The power shelf busbars losses goes up to 48 watts, and the hotspot is 77 degrees Celsius. This means that even in this condition, and consider these are already 27, 28, nearly 28 kilowatt, our unit, our configuration from busbar point of view would be able to work. Now, we wanted to do even more. We wanted to check a condition which doesn't exist, but it may exist in future, based on the capability of our 12 volts power shelf, where we have 3.6 kilowatt for each power supply. We're considering 5+1 redundancy, you get 18 kilowatt of power. So we wanted to see if you deliver 18 kilowatt, what we could do. But as we have seen, the busbar losses are already on the limit. So we have considered to kind of modify in the simulation only the busbars. As you can see here, there is, I think, where is the point? Yeah. This one here. We made the thickness of the busbars double, basically, and then the busbars are kind of folded so that you can still retain the 3 millimeters point. And this is a possible construction, maybe for higher power shelf with 12 volts distribution. And well, in this condition, basically you get 18 kilowatt per power zone. We have even increased a little bit the airflow from the server. We know that there is margin on that, so we went 20% higher, but it's still far less the maximum that the server could provide. So let's check results in this case. So again, 18 kilowatt per power zone, 1,500 amps, and the busbars, the vertical busbars, since they are thicker, they have basically the same losses as before, even slightly less, and a hotspot of nearly less than 80 degrees. The power shelf busbars are very red here, but they're still less than 90 degrees. So basically, based on busbars and configuration, an open rack could be able to deliver more than 30 kilowatt. So as a conclusion here, we could say that this finite element, simulation are really a key element if you want to explore, different configuration of the power rack with higher power. We believe is a good help to pre-assess what is feasible, what is not feasible. Obviously, everything needs to be supported then by real measurements. And Circle B, Rittal, and Bel Power are working together and can provide basically a complete solution for open rack. And we can implement together simulations to assess any type of rack configuration if required. And as we have seen as a conclusion, the 27.9 kilowatt maximum TDP configuration is possible from busbar perspective. This doesn't consider, obviously, the clips, which needs to be analyzed later, because the temperature of the clips may exceed the 105 maximum degree temperature of the clip themselves. So we need here a little bit the support from the clips manufacturer and to assess in this specific condition. In fact, we are starting also some discussion and cooperation with them. Again, as a last case, this is more like future thinking. We may even think to change these bus bars. Nobody limits us to increase the thickness of the bus bars and then being able to provide even more power. Even the bus bars of the power shelf could be slightly modified. We could make it thicker and still provide more power. I think the final message is that 12 volts distribution is capable to provide more power than what is currently declared. And I think this could enable future application. So, yeah, I think we are at the end.
Yeah.
We have only a few slides about Rittal, and that shows the material that we have used. So the standard open rack.
Yeah, we at Rittal built a standard open rack, and we used it for this simulation. I think you know the model. You will see it out there often. And yeah, and we won't to take too much time to this, but you see Rittal is able to provide with Bel Power and Circle B the whole system of OCP.
Yeah, so Circle B is a solution provider in Europe, and we work closely with manufacturers such as Rittal and Bel Power to make a complete solution based on the requirement of our customer. You can find these solutions in the marketplace as well, and you can also visit our OCP Experience Center if you're ever in Amsterdam.
And finally, Bel Power, we are manufacturing, designing and manufacturing power shelf, power supplies, and we are involved in OCP and working also with Facebook from the very, very beginning. So we have a series of different power shelf with different input voltage and output voltage. I think we are covering the whole range. And here in our website, you can find all the details. So we are open for questions.
Anyone?
Any questions? Yep, got one.
Are you considering the exhaust from power shelf and the servo into the simulation?
I'm not sure if...
And are you considering the exhaust from power shelf and the servos into the simulations?
The temperature?
Yeah.
You mean the temperature, the airflow, the temperature of the exhaust of the power shelf?
Yes.
Yes, we have measured this. The temperature increase across the power shelf at 18 kilowatt, it's up less than 30 degrees, the air. And in the server is maybe around 15 degrees in this condition.
Thank you.
Yeah.
Sorry?
Oh, we didn't report this one. This is the temperature of the air. It hit the bus bars, yes. Obviously, this airflow is not heating the bus bar. Actually, it's cooling the bus bar because the bus bars are still hotter. Yes, sure. This has been considered.
Any other questions? Okay, thank you.
Okay.
Thank you.